All right, we're here for our first episode of Going Deep 2005. We're here with Surendra Verma.
Hi.
And we're going to talk about Vista's Transactional File System. So what is a transactional file system? What does that mean?
All right, that's okay. Transactional file system. Basically, it's not a new file system. What we have done in Vista is we've taken our premier file system, which is NTFS, and we've enhanced it in very significant ways. So what we've done is we've taken this existing file system with all of its semantics, all the features that it currently has, and we've made all of them transactional.
Okay, now what does that mean?
So what that means is, if you've so transactions are basically a very fundamental concept in like databases, for example. What happens is typically when you work with a database, just to give you an analogy between a database, is you start a transaction, you call a system API to start a transaction, and then you work with the database and you do all your operations on the database within that transaction. And what that actually gives you is this ability to roll back your changes if you change your mind about it. So let's say, within a database you wanted to, let's say, you were working with financial accounts and you wanted to debit the account of one person and credit the same amount of money to a different person's account. You want to make sure that the debit and the credit either both happen or neither happens. You never want the system to be left in a state where you've debited the account and not credited yet, and the system may crash, and you don't want the system to crash in the middle state and leave things inconsistent. You also don't want, while this debit-credit activity is going on, you don't want other people to come in and be able to see this inconsistent state. If you know what I mean, the system is kind of inconsistent because you're not quite done with it until you've done both the things.
Understood.
So if you wrap the whole thing around a transaction, then what you're telling the system is that I want this whole debit and credit to be consistent and isolated. Isolated meaning others should not see that change until the change is complete.
Okay.
So you're telling the system you would like to see that happen. And you also are telling the system that no matter what happens, if the system crashes, the power goes off, whatever, the system should always return to a consistent state. A consistent state would be one in which if the transaction was still in flight, it was still in progress when the system went down, the system would essentially roll the transaction back. So it would roll back all the partially completed, the half-done work back out, and you'd be left with a state which would reflect no activity at all from this transaction. So there would be no debits and no credits in this particular case. So you get this consistency, and so this particular feature of everything or nothing is actually called atomicity, and the consistency is essentially guaranteed by the system enforcing these rules where everything happens and nothing happens, and then of course isolation. And there's another important property of transactions which is known as durability, which says if I'm able to complete this transaction, and which means I'm able to debit and credit, and then tell the system that I'm done, essentially issuing a commit call. You want to make sure that once you issue a commit call, no matter what happens, even if the power goes off, the machine crashes for any reason, you are assured that when the system does come back, that the entire transaction would be actually present. The effects of the transactions would be present on the disk. So that's called durability. The changes are durable. So there are like 4 key properties of transactions: A, C, I, D: atomicity, consistency, isolation, and durability.
Fantastic.
And so these properties have long been supported by databases for a long time. File systems have not had that, unfortunately. And there have been some prototypes, some research projects, and even some commercial projects where people have supported transactions in file systems. either in most of these cases, the support has been fairly narrow. So in some cases, people would support transactions for, let's say, only modifying an existing file and just writing all the contents to it, and just that part of it. In some cases, transaction support is present, but it's not broadly supported. So if you go across the network,
Sure.
and modify multiple file systems instances, the support is lacking. So it's never, so there, to my knowledge, there hasn't been a big broad support of transactions in a major widely spread file system in the past, and we are changing that in Vista. So for the first time, we are very happy to add this to Windows. So what we have done is we have taken this whole concept of transactions, which is ACID, and we have applied those concepts to the file system itself. So what you can now do is you can essentially start a transaction, and then you can just work on the file system, work on the various primitives of the file system. You can just create files, delete files, rename files, modify existing files.
As components of a single transactional unit.
Yes, absolutely.
Okay.
As components of a single transactional unit, you could just go and do arbitrary file system operations in NTFS, in Vista, and they would all be part of that transaction.
Excellent.
So they would be isolated from other applications until the transaction is complete. They would be atomic, so if the system were to crash, come back up, the transaction would be rolled back. So if you created, a bunch of files in a directory, you renamed a few directories, etc., all of those things would be undone. So none of the effects would be present. And if you do a commit, if commit succeeds back and you get a success code back from commit, the changes would be guaranteed to be present on the disk.
So in order to achieve the ability to roll back, you're taking a snapshot of an existing construct and then guaranteeing that if you don't complete, you will give them back. So is that how it works?
Yeah, roughly at a high level, that's how it works. Basically, what we do is the support is built right into the file system.
Okay.
So what that means is that we have had an opportunity to intercept every single API call that comes into the file system and modify it. And for example, if you are creating a new file within the transaction, we have an opportunity to intercept that create call. And remember the fact that the file wasn't present since it's a new file.
Sure.
If you're modifying an existing file, we have an opportunity to capture the previous state of the file. And then by recording these carefully, we are able to, in case of a rollback, put the old state back.
Okay.
Yeah.
Interesting.
And the rollback doesn't have to be just because of this. There's a system crash.
Sure.
There's actually an important case where the application may initiate a rollback. Let's say an application is working on, making a bunch of changes, and for any reason it crashes. If the application crashes for any reason, the system will essentially roll back the transaction. Or if the application decides to roll back the transaction because it finds that it's got into a state that it cannot recover from, then essentially it can make an API call that says, okay, I changed my mind. Can you please roll back everything I did, and I'm going to retry.
Sure.
So that option also exists.
Now, what about if I'm the developer of the application and I want to have the ability to say, let's say it's a document, and this person spent 2 hours writing something and hasn't hit save.
Yes.
And I want to say, all right, I have a transactional unit. I love what it gives me, but I also want to tell it to don't roll back, but try and capture where you are at the point of failure, and store that, or return, or at least. Is that a possible operation?
That's a great question, actually. The question is, what if I'm modifying a document, and I'm doing it within a transaction, and 2 hours have elapsed, and I don't want that 2 hours to be 2 hours work to be lost, but I do want to take periodic checkpoints, right? So what we envision is that people are going to periodically be committing their changes as they go along. So we don't actually envision people starting a transaction and keeping it around for like 2 hours, even though that what that does is it's kind of scary to keep a transaction around for that long, because for various reasons, transactions are not very well behaved when they're long duration ones.
Okay.
And typically what happens is that a long-running transaction can sometimes get rolled back by the system. So what transactions guarantee is that either everything will make it or nothing will make it. But there is no guarantee by the system that you can always commit when you want to commit.
Okay.
So you may have done a bunch of work, and when you want to commit, the system may say, "I'm sorry, I cannot commit it right now." And that usually doesn't happen, but the system can do that if it is out of resources, for example.
Okay.
It is simply unable to fulfill that obligation. So I shouldn't say obligation, because there's actually no obligation to commit. There's only an obligation from the system to ensure that either it'll commit or it'll roll back. It'll never be left in the middle state. So yeah, so as a programmer, you want to be aware of that, and you want to keep your transactions relatively short in duration.
Fantastic. So what are some examples of when I'd want to use transactions versus the traditional file system mechanisms?
Okay. So basically, anytime you update a file and you care about your file's contents, you want to use transactions.
Okay.
So the reasons are very simple. File systems have never given any sort of haven't given too many guarantees in terms of what gets updated, how and when. For example, you can open a file, and let's say you have a file that has some data in it, and you would like to go and change parts of it. If you want to absolutely make sure that you are never left in a state where while you're changing the file, something bad happens, your application crashes or your system crashes or whatever. If you never want to have a state where you're left if you never want to be in a situation where your file is left in an inconsistent state, you want a transaction. The way the file systems work is you open a file and you start writing to it. As you write to the file system may write some of these pages to the disk, or may not. Certainly you can call a file system API and say flush my file to the disk at that point. And at that point you know it's on the disk. But you don't know until you call flush that nothing has been written yet. There's no way to say please don't write anything until this flush.
Okay.
So while you could be updating the file, you are actually exposed essentially. Your state is partially saved, potentially.
Right.
So you really have no easy way to atomically update files. So typically what applications do, they do not update files in place. What they do is they make a copy of the file. So they'll create another temporary file with some other name, a temporary name. They'll put the new data into that file. So they leave the original file unchanged. And then they rename the original file out to yet another temporary name. And then they rename the new data, which was in this temporary name, over on top of the real name of the file. So that's how they're basically creating two files and then renaming in, so that they never actually modify the data in place. So that's typically how people end up updating files. Not only is this cumbersome, but it's actually not fail-proof, because there are again windows here where you could be in various states. You could be in a state where you've renamed, your existing file out to a temporary name, while your new data is still sitting in yet another temporary name, and you have two different temporary names.
Understood.
And there is no file on the system anymore with the name that you have. So when you come back up, you have to be aware that you were in this state, and then be able to recover by renaming either of the two files in. The way Office typically handles this is through, they put a bunch of UI on top. So when you go into Word or any application, it prompts you and tells you, you may have lost files, and here are the previous versions, and which version would you like to, use today.
Sure.
So there is application level logic. What we have done is we have taken all that out and put that into the system.
Nice.
So applications don't need to worry about leaving things inconsistent anymore. They can simply do their work, and when the system comes back up, the data will be consistent.
Wow. That's excellent.
Yeah, thanks.
Cool.
Yeah.
So, what happens? So, can you explain concurrent operations and transactions?
Sure, absolutely. So, with transactions, there is a concurrency model that we have developed, a locking model that we have developed to ensure a consistent and predictable, execution order.
Sure.
So, the basic issue is what happens if there are multiple applications that want to modify the same file or same set of files at the same time.
Mm-hmm.
And today in Windows, there is the notion of file sharing bits. So you can actually say you can open a file and you can specify whether you want to open it for sharing, with readers or with others,
mm-hmm.
for reading, or sharing with others for writing, or none. In transactions, what we have done is we have kept that model. So certainly, whatever sharing modes you specify will be honored. But in addition to that, we've added a few other locking modes, which we call transactional locking. What we do is, essentially, we ensure that at most one transaction can be working on a file for modification at any one point. So, let's say a transaction T. Maybe I can draw some pictures of my board.
Please do.
Easier to explain.
Sure.
So, just trying to draw a timeline here. So let's say that transaction T1 in this timeline. So this T1 open F, open file A, read write.
Okay.
And then somewhat later, trans T2 opens the same file for read write or just write. This operation is failed since this read write conflicts with that read write because these transactions are different.
Okay.
However, if the same transaction T1 were to open file A again for read or read write or write, that would succeed. Since this transaction T1 and T1 are the same. So they are compatible with each other.
Understood.
But T2 being a different transaction is not allowed to open for read write. However, if this transaction T2 were to open it for simply reading, were to do open file A simply for reading,
mm-hmm.
this would succeed.
Okay.
And not only will it succeed, this handle that will be returned, the file handle that would be returned,
sure,
would be an isolated handle. So this handle would not see changes that are made by this transaction.
Understood. So that would be where you have the initial state.
That's exactly right.
Okay.
And the initial state would be used to provide isolation for this handle.
Fantastic. Very cool.
And the isolation, so yeah, so the isolation works essentially in the following way. This file handle, since the file handle is open within a transaction, a different transaction, this file handle saves the state, isolated state, along with the handle
mm-hmm.
forever, essentially for the duration of the file handle. As long as the handle is open, you continue to see that one consistent snapshot
okay.
of the state as of the beginning of transaction T1.
Now let's say, is there a way for the holder of the handle to be notified when transaction T1 is complete?
Yes, it's possible. What they can do is they can effectively enlist in the other transaction and wait for an outcome for the transaction to complete.
Okay.
And at that point, they can go and reopen a handle, and then they get the new contents. Absolutely.
Understood. Yeah. So not real time, because that would do isolation, makes it impossible to have real time
right.
Display of data changing. That's the whole point. I understand.
Right.
But to be notified when the transaction is done, and then say, okay,
right.
then in the background reload it.
Correct.
So that my
Absolutely.
up in user land, they see the new file.
New file. And there is another thing I must mention at this point. There is also the notion that you could open this handle without the transaction. So I could just change this same example for a second.
Sure.
Same example for a second, and simply just remove this transaction and just open the file without a transaction.
Okay.
Just like you would today without transactions. So in this case, this file A is being opened for read-only, completely outside of transactions. This handle is still isolated. So we isolate by default. But in this case, the behavior is slightly different from what I just talked about, in the sense that it is isolated for as long as transaction T1 is active. As soon as T1 commits, the next time this file handle is used for any kind of I/O for reading, the isolation is over. So the effects of transaction T1 are visible. The new changes are visible
in the same handle.
In the same handle.
Wow. Okay.
And this is done essentially for applications that are not opening in transactions.
So you interoperate fine with the old model.
In a way we operate fine with the old model, except the caveat is that your state changes are visible as soon as the commit occurs. So essentially we are delaying all the changes, batching them up up until the commit, and then suddenly showing them. Not that many applications open read handles and allow sharing with writers, but clearly this is the case where someone is sharing with writers and has some other way of synchronizing with writers.
Sure.
And they expect changes to come at them. So
fantastic.
And if they don't want to see that changes happen to them suddenly, they can open with without file share right specified. So they can basically say, look, I don't want to share with writers because I don't want to be surprised.
Now, let's going on to the programmer level.
Okay.
You have written a public API, clearly, and it's part of WinFX?
Yes, that's a great question. So what we have done is, certainly the API does exist at the WinFX level as well. So there is actually multiple layers at which the APIs exist. So we have APIs existing at the Win32 level for transactions. And then we have APIs that exist, that layer on top of those in the old ATX, the DTC style COM plus COM transaction model. And then there's also a set of APIs at WinFX level, which are under the system.transactions class.
Okay.
So folks can go check that out. There are actually examples, there are actually blogs out there that talk about the use of system.transactions for TXF.
Okay.
And they can and people can see how to use system.transactions to go
in managed code.
In managed code.
Fantastic.
So people can actually have managed code, and they can have they can actually interrupt with managed code for transactions and Win32 for file I/O, all at the same time.
Fantastic.
And they can also have Win32 for transactions.
Sure.
And that is somewhat limited in scope.
What do you mean by that?
Win32 level transactions they're great when you want to do updates on your own machine, but essentially they're limited because you cannot involve other arbitrary resource managers. I would encourage people to go use system.transactions or the old ATX for transactions.
Sure.
I would really not encourage the other one.
And if you're a C++ programmer, you can still write in native code and then still interact directly with that.
Yeah, you could write in native code, and in C++ you could use OLATX for transactions, and then interact with Win32 file I/O, and you're completely unmanaged.
Yeah.
Certainly, that's possible.
Sure.
One thing I did not mention was that we support full two-phase commit, so you can actually do distributed transactions. You can actually start transactions at system.transactions level or OLATX level, and do some file I/O, and do some, for example, SQL Server database updates, and the complete set of updates between the file system and the database are coordinated in a single transaction, single distributed transaction.
So that brings up an interesting question. How do you? So if I'm interacting with a remote construct like a database,
right?
And I'm this transaction unit, and things are happening. I'm doing a little bit of I/O. I'm asking SQL to do a little work for me. All of a sudden, electricity goes out.
Right.
How does SQL know that it needs to roll back the transaction?
Okay, good question. Let me make a picture and kind of explain it.
Sure, please do.
Okay. So that requires the use of a distributed transaction coordinator, DTC.
Okay.
So DTC is this this product that we have shipped, in Windows for many releases now. Okay. It already has interfaces where he interacts with SQL Server, and SQL Server knows how to participate in the two-phase commit protocol.
Okay.
And so they actually talk. There's a protocol here, and a two-phase commit protocol between the two. And we have, if this is the kernel boundary, we have TXF in the kernel, and TXF itself essentially has the NTFS part, which we call TXF. There is a Kernel Transaction Manager, which, by the way, is another full two-phase commit capable transaction coordinator.
Okay. That's new in Vista.
That is new in Vista.
Supports this whole paradigm.
Yes, absolutely, and that makes all of this work seamlessly. And we have a logging system, CLFS, which is a full high-performance transaction logging system, which is not only used by NTFS for transactions, but it's also used by the TM, Kernel Transaction Manager. By the way, it's also used by TXR. I'm not sure if people understand this, but the registry itself is going to be modified in Vista. Will support transactions natively.
Fantastic.
Yeah, absolutely. That's actually very cool. So even TXR uses CLFS. So all of these guys use CLFS. And CLFS also has interfaces here, both at Win32 level and managed level, the layer on top. So you could actually directly call CLFS and use it for your logging needs of any kind.
Interesting.
Absolutely. So it's actually very cool. We have exposed the transactional high-performance transactional log that we wrote for our purposes. We've exposed them, to the world essentially through APIs. So you can just take advantage of it as well as TXF internally does.
Outstanding.
Yeah, I think we're very excited about that. That is actually shipping in R2, the Windows Server R2.
Okay.
CLFS along with its interfaces.
So
do take a look at that.
Fantastic. Is there any plans to have TXF in Windows 2003 at some point?
We don't have any current plans on that. It's a little hard.
Sure.
To support that level.
Okay.
Yeah.
Fair enough.
So going back to the original one, so we do have this Kernel Transaction Manager, which is a full two-phase commit protocol, which exposes with APIs here for transactions. And we have a layering of DTC on top of this. So essentially the transaction primitives here get remapped over to KTM. And we have worked very closely with the DTC team, and they have done a lot of work, with us in order to support our scenarios efficiently. And so, going back to the original question of how do you involve like something like SQL Server and TXF in the same transaction? So essentially, the application sits over here, and this is a very high-level picture. Sure. And the application would interact effectively with DDC, one of many ways, either using the managed API set, in which case the application is a managed application and it uses the system dot transaction implementation, which internally would use DDC.
Okay.
Or the application could be unmanaged, and in which case they would just directly use DTC APIs to start and commit transactions. And so the application would essentially start a transaction, DTC, with DTC. Then it would go to SQL Server, and it will do essentially some transactional work and carry the transaction with the request. At that point, SQL Server will talk to DTC and essentially get itself involved in that transaction.
Okay.
So DTC at this point knows that there is a transaction in which DTC is SQL Server is a participant. The application next would come and call an API, a new Win32 API, which would essentially take a DTC transaction and convert that into like a kernel level transaction.
Okay.
And once it has the kernel level transaction available to it, it will call TXF with it. So then TXF will essentially, just like SQL Server talks to DTC, TXF talks to KTM and says, here, I'm interested in this transaction.
Okay.
So now KTM knows that there is a participant in its transaction. And by the way, the KTM transaction is a part of the original DTC transaction as like a lower level transaction.
Okay.
They're layered on top of each other. Meanwhile, the application could also go and talk to TXR, for example, and the TXR could also talk to KTM. So now you have this picture where you've neatly layered various components. You've got a transaction here that's layered on top of this one. And this transaction manager essentially will coordinate all the kernel resources and would neatly layer below the DTC transaction, which would in turn coordinate with everything else, such as SQL Server on the same machine or other machines.
Fantastic. And so you mentioned earlier about the issue with long-running transactions.
Correct.
SQL, if something did happen,
Right.
and DTC somehow disappeared,
Right.
then SQL would know that, okay, I know that this transaction is not complete yet,
Right.
and it's been, I don't know, an hour.
Right.
It's done. I'm rolling back. So that kind of logic?
So yeah, so the system handles all sorts of failures at all sorts of levels. For example, it's possible that, well, you hope that DTC doesn't go away.
Sure.
It's a critical system component.
Sure.
But let's say that SQL Server goes away.
Okay.
DTC would detect that, would say that one of the participants is gone, has died. It will essentially roll back the transaction.
By letting everyone else know that it's finished.
Correct.
Okay.
So it will roll back the transaction it'll tell KTM to roll back the transaction, which would then roll back TXR and TXF. And when SQL Server comes up, eventually, as part of its recovery, it may go and talk to DTC and say, what happened to my transaction? And DTC in its log would remember that SQL Server was a participant at a particular point and had gone away. And so DTC would then at that point tell SQL, look, you went away, so I just went and rolled everything back, so you should just go and roll the transaction back in your state right now. So then SQL would go roll back at that point. So that's all done through this two-phase commit protocol, which is something that's people may want to go read up on if they're, that's a very well-known concept. It's been there for a long, long time.
Sure. But it's not necessarily being used in an innovative way as what you've done with TFS.
We have certainly extended that concept into the system itself, into the kernel, and we have certainly added a lot more participants, a lot more parties to that mix, such as the file system and the registry itself.
Now, are there security implications with using transactions?
There shouldn't be security implications using transactions.
I mean, in the positive direction.
Yeah. Oh, in the negative and positive. I think it should be pretty neutral, security neutral, and we do expect the effect of transactions to not. Yeah, we don't expect it to affect security in one way or the other.
Sure. Because I was thinking in terms of it being a closed construct.
Yeah.
If you could get in and somehow, so if transaction 1 is happening and I somehow am able to get into that transaction context and maybe change, just read from the file and then split somehow. That's just crazy. There are some interesting implications that way. Certainly, there is a security model that we have for transactions to ensure that people using transactions can ensure the integrity of the transactions and not have malicious people join their transactions and roll back on them maliciously. Sure.
So the KTM model certainly has the notion of ACLs, and DTC itself is pretty hardened from security point of view in terms of malicious attacks.
Fantastic.
So we shouldn't expect security issues to come out as a result.
No. Now, are there any performance implications of transactions?
Absolutely. They cost.
Big cost.
They cost. Transactions have a cost. Essentially, when you're doing a transaction, you're getting a few guarantees. You're getting essentially the two biggest guarantees that cost are atomicity and durability.
Sure.
Atomicity means that every time you make a change, we need to capture the snapshot, the previous image. Mm-hmm. And we need to capture it in a way that if your new change makes it to the disk, that the snapshot also better be on the disk. So we can always, in all cases, roll it back. Mm-hmm. So you do have a cost. The cost, we like to compare the cost of transactions with that of what you would have to do in your application, perhaps, to try to approximate a similar behavior, which would be, doing the renames of files, for example, or flushing of files and hoping to narrow down these windows, or maintaining a log in your own space to try to keep track of the changes to roll things back. And certainly, compared to the kinds of things people would have to do to achieve the same behavior, mm-hmm. we believe that we should be able to deliver a higher performant solution, simply because we are in the system.
Sure.
And we have a lot more ability to optimize.
Absolutely.
In the system.
Not to mention probably a better cumulative understanding of what you're doing than, say,
Absolutely.
A single developer trying to solve a solution.
That is perhaps true as well. Cumulative understanding and the amount of knowledge we have. For example, we are so tightly integrated with NTFS, and we are part of NTFS, that we know exactly we can take advantage of all the interesting states in which things are in memory versus on the disk, and we can delay writes to the extent possible. In some cases, because we know that certain other writes haven't gone to the disk yet, and that information is definitely not available to anybody in the system. Certainly not outside the system, but even within the system, like a filter driver sitting, a mini filter running on top of NTFS would not have that information.
I mean, and it's important just to stress in this case that we're talking about a new kernel component, a new Windows kernel component.
Correct.
So, just to clarify, that's why we have a better understanding.
Yes.
And perhaps one could say a better advantage, but it's not. That has nothing to do with it. It's the fact that it's a new kernel component, a new kernel.
Right. Absolutely.
So, I'm very impressed. Very interesting. What has your feedback been so far from devs?
It's been pretty good. I mean, we have. First of all, we are actually pretty new, so we haven't really gone out all that much. We've been kind of keeping it under the wraps for a long time. And we went out in the PDC and talked about it. There's some interesting response on the internet, in the blogs out there. Sure. There's an interesting buzz going around. We have a few people inside Windows itself that are relying on it in the system, in the Windows system itself.
Fantastic.
To take advantage of this, to make some of the common Windows scenarios more reliable.
Absolutely.
So that's pretty exciting.
Totally. Well, thank you very much for your time.
I
really
you're
appreciate
welcome.
it.
My pleasure.
And great luck. Good luck. This is very, very interesting stuff. And we'll make sure to put on Channel 9 where developers can get more information about the API.
Okay.
And hopefully we'll see you on Channel 9, maybe interacting a little
bit.
Sure, you have plenty of time.
All right, sure, yeah, why not?
Thank you very much.
We'll look forward to it. Thanks.